Hey, hello and welcome back everyone. Last video of this semester, moving on to surface areas and volumes obtained by rotations. Now, a lot of times this volume section is a topic in a first course in calculus. So that might be a little bit of a review for some of you, but there's good relationships we can make between the volumes by rotations with the surface areas that we're going to be considering today. And so with that said, let's start with some surface areas. And the surface areas we're going to work with are going to look like the following proposition. We're going to have rotationally symmetric solids, which is going to be the same as what you had if you've seen volumes before. We're going to consider on our xy plane some curve. And to compute the surface area, of course a curve by itself has no area, we're going to rotate that curve around an axis, and then we're going to compute the surface area of this shape that results. Now the reason why surface areas themselves are not included in Calculus 1 is because the calculus that you need to compute them just ends up being harder. You'll notice what's happening here. We have a square root of 1 plus a square. More or less, trig sub is quite common. You can imagine if this f prime were like linear, right? And this were the root of 1 plus x squared, then trig sub would be what you wanted to use. Now, other things may show up where you don't necessarily have to use trig sub, but because of that square root and a square inside of it, trig sub ends up being a lot more common. Anyway, we basically have 4 situations that I'm providing in this case, dependent on how the function that we started with on our axis is defined, right? A function of x is kind of our natural functions that we work with, like a parabola, for example. A function of x could be rotated around the x-axis. If you rotate it around the x-axis, you're getting something like that in your rotation. Or it could be rotated around the y-axis. If you rotate around the y-axis, you're getting a shape that looks like this out of your rotation. Of course, the surface area of those two shapes are going to be different because the shapes themselves are actually different. You know, the second one's like a cup, where the first one is maybe closer to like a horn or something. Okay, so at least as far as functions of x are concerned, we're thinking about cases 3 here. If we decide to rotate the function of x around the x-axis, let's draw that out again as maybe a parabola. We're going to go around the x-axis and say we have something like that. My parabola pointing in the downwards direction as well. We compute the surface area as, well, it's 2 pi. 2 pi is just coming from us more or less calculating the circumference of one of these circles. Recall the circumference of a circle is 2 pi times a radius. And so the circumference 2 pi f actually ends up being the radius of that circle in this case, because if I start at the center and go up to the height of the function f, there's my 2 pi r. So we have a 2 pi radius here. And then this should actually feel familiar coming from the last section that we covered. This is the arc length computation. Technically, it's an arc length differential. And so what are we doing is we're computing each circumference of a circle as I've drawn it here, and then we're dragging, because of this arc length, we end up dragging that circle all along the area that we draw out. So we have like infinitely many of these circles that are getting dragged all along the shape, and the circumference of a circle, if you drag it through space, is going to trace out a surface area. And so that's why it works. The function of x rotated around the x-axis. If we think about a function of x maybe rotated around the y-axis instead, we actually are going to have a very slight modification to our surface area. And that's going to be because our radius is no longer described by the height of the function. If I'm playing against the y-axis here, what is the radius maybe of one of these circles? That radius is simply the value of x that I'm at, right? If I drop down the distance from the y-axis, the radius is simply my value x. And so in this case where we rotate around the y-axis, we have 2 pi r still, 2 pi times the radius, to recover kind of the circumference of a circle. And then we're going to drag that circle along the entire arc length to actually get the entire surface area. And so we still have the same arc length differential. The only difference between choosing the x-axis versus the y-axis is what does our radius actually become. When we're talking about the x-axis, the distance from the x-axis is the height y, but the height y is described as long as we have a function of x by f of x. And then if we're rotating around the y-axis, our distance from the y-axis is just described by x, the actual distance from the y-axis. So those are the two differences there. And in fact, you can imagine in this case where you have a function of y rotated around the x-axis, you can imagine I've just basically played a game where I've swapped every x for every y. And so if we compare these two formulas, they're the exact same, except I've swapped every x for every y. And then the same thing actually is true if I have a function of x around the x-axis or a function of y around the y-axis. I mean, the formula is not on the screen yet, but you can basically see when I scroll down, this is going to be the same, where I just swap every x for every y. And you're going to get the same formula just in functions of y. So there's our final formula. We have a function of y rotated around the y-axis. Okay, now understandably, I did give you a little bit of intuition about how these formulas show up. You take a circumference and you drag it along the arc length. I also have the true proof in the book. I'm going to go through it slowly here just in picture form, because in this proof the pictures do show 1,000 words. You're going to dissect the actual surface you're looking into very many small, they're not quite cylinders, these are called frusta or frustum. So a frustum is like a portion of a cone. So that's why the arc length is showing up, because if you decided to look at each of these side lengths, they're not actually flat, right? These sides are a little bit bent up or down, and so that's why we have a frustum instead of a cylinder, but you're going to calculate the surface area of a lot of these small frusta and then add all those surface areas together. But you can see basically when we do divide it into very many pieces that you are just basically calculating the circumference of a circle and multiplying it by an arc length to recover the answer. Okay, so with that said, let's actually go through some examples of each of these cases. I kind of have what I call a comprehensive example of each of the surface areas. Maybe I want to compute the surface area generated by revolving the curve root 1 minus x around the x-axis over the interval 0 to 1. I know I already have a picture of it on the screen, but let's say that maybe I didn't know how to actually obtain that picture right away. What we're going to do is we're going to plot that function, root 1 minus x. What does root 1 minus x look like? Well, definitely at the x value 1, it's equal to 0, because I have root 1 minus 1, which will be root 0. And then because x is negative, it's going to be moving to the left more or less as a square root, right? Normally a square root function would move up and to the right, but because I have a negative x, we're actually going to move up and to the left. And at the left-hand side here, this is a height of 1 on the y-axis. Anyway, if we want to kind of think about what this would look like if I'm revolving it around the x-axis, all I'm going to do is give myself the ability to draw a bunch of circles in the approximate shape of that function, and kind of connect them in the negative direction as well. It gives you a good idea of what you're actually looking at when you want to compute the surface area. Anyway, let's remember our formula. So our formula, when we have a function of x around the x-axis, the surface area formula, well, it's always going to be, we're going to look at circles here, right? So let's grab ourselves a circle, and we'll ask some questions about the circle. What is its circumference? Well, the circumference of that circle is going to be 2 pi r, but in this case, what is r? It's 2 pi. The radius is going to start, because it's going to be this distance here. It starts at 0 down here, but it ends up at the top here. What is that top? That top is just the description of my function. It's f of x, and so it's 2 pi. F of x is my circumference, and then the arc length formula is always the same. Arc length, no matter what, will always be root 1 plus f prime squared. And so our formula here is going to be 2 pi r, but we don't have r, we have f of x, and then the arc length formula 1 plus f prime of x squared dx, and then we're going to have to integrate over some lower x bound here all the way to the upper x bound there. That's going to be 0 to 1, so I have 0 to 1 here. If I actually go ahead and compute f prime, well, I'm just going to use the power on f prime. It's going to pull down a 1/2, and then I'm going to end up with 1 over 1 minus x, and then the negative comes from a chain rule. So it's a power and a chain rule together, and I'm plugging that in, of course, for f prime. And then f of x is just coming along for the ride as root 1 minus x. At this point, all I have to do is simplify and integrate. So let's see what that looks like here. I can take this square and put it on both terms there. That's going to give me a 1/4 from the 1/2 squared. So it's going to be the square root of a square in the denominator, so it'll just be 1 minus x. Simplify a little bit more because I've got a square root and another square root, so we can go ahead and grab this 1 minus x and actually put it inside of a single square root. And then it's going to have to go ahead and distribute to both terms here. When I distribute on the second term, it's just going to cancel with the 1 minus x in the denominator. We'll end up with 1 minus x plus 1/4 under that square root, or in other words, 5/4 minus x to 1/2 power. We can just use a u sub if we want. U sub with u equals, we have a function in parentheses, right? 5/4 minus x. du would be negative 1 dx, so we just need to pick up a negative sign here. There it is. And then we'll use the power rule where we add 1 to 1/2, and we divide by the new power. So we'll have 3/2 in the power and a 3/2 in the denominator. A little bit of simplification. If I plug my bound 0 and 1 in, plugging a 1 in gives me 5/4 minus 1. Plugging a 0 in gives me 5/4 minus 0. Simplify that a little bit more. This is as good as it's going to get for a lot of these. They're never going to look beautiful, but they'll always look okay, I guess. Or you can plug that into a calculator, you get about 0.533. Of course, 0.533 is in units squared. If we want to do the surface area, the surface generated by revolving the curve defined by g of y is y squared minus 1, and y goes from 1 to 2 around the x-axis. We can do that as well. Let's just draw it really quick. How do I draw a function of y? Well, something like y squared minus 1 in my head. I'm just on the right-hand side going to draw x squared minus 1. That looks like this. And if I'm swapping x for y, I'm just going to mirror that over the diagonal, and now I'm going to get that function instead. So that's my function, g of y equals y squared minus 1. We're going to go over the range of values starting at 1 and ending at 2. So here's the 1 for y, here's the 2 for y. So we're going to grab this range, and we're going to revolve that around the x-axis as well. So we've got this shape here. Now we're going to calculate the surface area of. If I want to find my integral for this, well, we always have 2 pi. Let's ask ourselves what the radius is here, the radius of one of these circles. Everything's in the variable y, right? So the radius of that circle is just the height of the function. The height of the function is just y. And my arc length differential is the same as always. It's going to be root 1 plus g prime of y squared dy. I'm going to run over my bottom and upper y bounds, 1 to 2. So that'll be my surface area formula here. If I actually compute the derivative on g, of course, the derivative of y squared minus 1 is just going to be 2y. And so I'm plugging that into the arc length formula. It'll simplify to 4y squared. And then if I want to integrate this, I'm not actually going to pull this y inside because I'm going to be a little bit more clever and ask myself, hey, could I already do a u substitution? I have a quadratic term here. What's the derivative of a quadratic? It's always a linear. If I let u equal 1 plus 4y squared, then du will be 8y dy, or in other words, 1/8 du will be y dy, and we have exactly y dy in our integrand already. There's my 1/8 that I'm paying the price of. Just going to use the power rule on that 1/2 power. That's going to give me a 3/2 in the numerator, 3/2 in the denominator. I'll then plug in the 2, my upper bound, and I'll plug in the 1, my lower bound. Simplify. We've got another collection of not great looking things, but in this case, final answer 30.847. Look at another example. We've got a surface generated by revolving the curve defined by log of x here over the interval 1 to 3. We're going to revolve this one around the y-axis, right? And so thinking back, I know I have the picture drawn already, but if I just wanted to draw this myself, there's log of x. And let's grab it over the interval starting at 1 here, ending at 3 there. And now we're going to revolve around the y-axis, and so we're going to draw, fairly good circles revolving my curve around the y-axis. If we're curious about our formula, we always have 2 pi, and then the radius. What's the radius here? Well, if everything's in the variable x, the radius, the distance from the y-axis is simply x. And we have the arc length differential 1 plus f prime of x squared dx. Minimum value for x here is 1, maximum value for x is 3. What is the derivative of log? Well, the derivative of log is 1 over x. We're going to go ahead and simplify this 1 over x to be 1 over x squared. How would we actually compute this integral? Well, we're going to compute it by, we don't have the ability to use u sub on this, but we can take this x, pull it inside at the price of a square because it's coming in a square root, and then that square is going to distribute to both the 1 and the 1 over x squared. It turns out in this case we're going to have root x squared plus 1. Now let's think critically. Do we know how to solve integrals of square roots of quadratics? The answer is yes. Square roots of quadratics is always trigonometric substitution. In this case, we already have a completed square. We've got x squared plus 1. We're going to end up using that x is going to be tangent of theta, which makes dx secant squared theta d theta. How does that simplify our integral? Well, we're going to get 2 pi integral square root of tangent squared theta plus 1 secant squared theta d theta. We're going to get 2 pi integral. Because tangent squared plus 1 is secant squared, I'm going to take a square root of secant squared. I'm going to end up with secant cubed theta d theta. Now that's not the easiest thing to integrate, but maybe it's one of those you've memorized by now because it is a little hard to integrate. It ends up being secant theta tangent theta plus log of secant theta plus tangent theta plus c. If you make reverse substitution, that theta will be inverse tangent of x. Everything ends up simplifying here. This integral actually shows up often enough. I would advise maybe that you do memorize what it's equal to. It's just so common for arc lengths and surface areas. But anyway, that integral is equal to that collection of terms. You use trig sub to get there. And then you find out that the surface area, well, we got our antiderivative. It wasn't great, but we have it. We're just going to evaluate on the lower and upper bounds. So we'll plug in a 3 for every case of x, and then we'll plug in a 1 for every case of x, and simplify a little bit. It's not great, as always, but you can plug it into your calculator, get 28.3. The last case, let's think about the surface area of this surface, root 4 minus y squared, from y going from 0 to 2 around the y-axis. What does that look like? If I didn't already know how to do it. Well, if we think about the equation, x equals root 4 minus y squared, I can square both sides. I get x squared is 4 minus y squared, and I can solve for x squared plus y squared, and that's going to be equal to 4. This is just a circle of radius 2. But because it's, a function of y, and we only have the positive function of y, this ends up being the right half circle of radius 2. So you get the right half circle of radius 2, but then you look only in the range starting at 0 to 2 for y, so that's just going to be kind of the upper right quadrant of that circle, and then it's rotated around the y-axis. It'll rotate as a series of collected circles that push out kind of this upper hemisphere. So you get this lovely looking hemisphere that we've drawn in the middle for you. So here we're actually just calculating the surface area of a hemisphere. Ideally, it aligns with our geometric intuition. Let's go ahead and see if we can do it. We need a derivative of this. Well, we're going to calculate that using the power and chain rule. dy on there. Power rule is going to bring me a 1/2, keep everything on the inside the same. Now to the minus 1/2, and then I'm going to multiply by the derivative inside, negative 2y. A little bit of simplification, we're going to have a negative y divided by 4 minus y squared to the 1/2 power. So there it is. Looks like I'm missing a little square up there. No big deal, I definitely included it on the next line. So we're going to go ahead and square that term. We get y squared over 4 minus y squared. And as before, we've got two cases of square roots. We can combine them. That's going to bring my 4 minus y squared to the inside, and that 4 minus y squared will distribute to both terms here. They'll end up canceling with that one. We'll end up with 4 minus y squared plus y squared, also known as square root of 4, or in other words, that this surface area is constantly increasing from 0 to 2. So we'll just integrate the number 1 from 0 to 2. That's just going to give me a value of 2, also known as 8 pi. Now let's recall our formula for the surface area of a sphere of radius r is 4 pi r squared. What happens when r is equal to 2, like our case? We get 4 pi times 2 squared, also known as 16 pi. But we only have a hemisphere, so we're going to go ahead and divide that by 2 and get 8 pi. So nice to confirm that our surface area formula works when we're dealing with spheres. So there's surface areas for you. Now we can move on to volumes, which perhaps you have actually seen before. These volumes are going to get constructed in very similar manners to those of surface areas, right? So if we maybe decide to rotate a region, maybe a region between two curves, let's say this is one function calling f out, and another function I'm calling f in for outer and inner, and maybe I want to rotate those around the x-axis. So rotate your inner function around the x-axis, rotate your outer function around the x-axis. What you get is a shape that looks, approximately like what I've drawn here. It's hollow in the middle, and it has, filled in between these outer and inner functions. We can calculate the volume of those more or less by asking what would the volume of a very thin cylinder be, and then we just drag that very thin cylinder all along the sides. So what would the volume of that very thin cylinder be? Well, it would be the area of a circle, which is pi r squared, but there's both an outer circle and an inner circle. So we're going to subtract pi r inner squared, and then we're just going to go ahead and drag this circle all along the x-axis from some minimum value to a maximum value. Now, just like before, what is the actual radius of these circles? Well, the radius of the outer circle is simply f out, and the radius of the inner circle is simply f in, and so we end up with pi f out squared minus pi f in squared. And we're going to integrate this all along from some minimum x value to a maximum x value dx. And if I want to, I can just go ahead and factor out pi. And here I've included absolute value signs just in case you choose inside and outside functions backwards. Now in the case that we have a function of y that we want to rotate around the x-axis, things are going to change a little bit, right? So now let's assume that my function is a function of y. I still have an outer g out and g in, and I'm still going to rotate these around the x-axis. But the question is, what's actually going to happen with my radiuses? Well, my radius is no longer the height of the function, because g out is a function of y and g in is a function of y. Those are describing x values, and the radius is not an x value. The radius in this case is a y value. And so what you get is the radius y, and then you have to recall that we're actually integrating in the y direction, which means we're drawing a lot of parallel lines, and they're all perpendicular to the y-axis if we're actually cutting our shape up. And so somehow we have to use the radius that occurs in the y direction along with all of these integrations, these parallel lines, to actually give us a volume. And the right way to do this is what we're going to do is construct a cylindrical shell whose edges are at each one of those parallel lines. So that's one cylindrical shell. Another one will occur slightly inside of it. And we're going to add all those cylindrical shells together. So when it's this shell of a cylinder, has an area of 2 pi r. It's the circumference of a circle times the height of that shell. Well, we can find the height of the shell because we do have the height, meaning how long does it take to get from one side of the cylinder to the other. Well, we have, those are in the x direction. We have a couple functions which describe x values here. We're just going to take the outer function that describes an x value and subtract the inner function. That's going to give us a total length of a cylinder. And so what we have here is 2 pi r h. We have a lot of cylinder areas that are then all added together from some minimum y value up to a maximum y value. Now it turns out that cases 3 and 4 are just the other swapped x and y versions of this, the same way we had swapped x and y versions for surface areas earlier. So they're all basically the same as long as you pay attention to which case you're in. You have a function of x rotated around a specific axis, function of y rotated around a specific axis. Just find your specific case and you'll have the right formula here. As before, even though I kind of described the proof of each of these, I'll just slowly scroll through the images I've provided so you can see how each of these volumes are dissected into their very small parts. So here I've got a lot of these kind of discs or washers. Sometimes we'll call these the washer method, that separate a specific volume into its total size. And if I keep scrolling down, we'll see if we decide to rotate in the other direction, then I can actually separate things into cylindrical shells or nesting cylinders that fit inside one of another. Right, the washers fit beside one another, the shells fit inside each other. We're going to get our way through the nice examples here, where I have one example of each of the volume calculations we could make. So let's say I want to find the volume of the region between the curves root 1 minus x and 1 minus x over the x interval 0 to 1, revolved around the x-axis. How could I graph this if I didn't already see it? Once again, well, root 1 minus x, we actually encountered this one before. That's going to be a square root in the negative direction that intersects 0 when x is equal to 1. As well as 1 minus x is just, negative slope linear curve with y intercepts 1. And I'm going to take the region between them, and I'm going to take that region, I'm going to rotate the entire region around the x-axis. So I'm going to ask questions about the volume of that object. And if I look at the previous proposition, it says that my volume is going to be pi times the integral of f outer squared minus f inner squared dx from x minimum, in this case 0 to x maximum 1. Well, I can write out f outer, that just happens to be, I'm going to look at my curve to verify, yeah, that happens to be root 1 minus x, and that gets squared. Then I subtract 1 minus x, which also gets squared, dx, that's integrated from 0 to 1. I simplify a little bit more, it's going to give me 1 minus x minus 1 minus 2x plus x squared, dx from 0 to 1. And finally, that'll be pi integral 0 to 1 of, well, I have 1 minus 1 will cancel each other. And then I'll have negative x minus negative 2x will give me a positive x, and then minus x squared dx. If I go ahead and scroll down, you can see I've got the same computations here, x minus x squared. Power rule on that will give me an x squared over 2 for the antiderivative of x, and an x cubed over 3 for the antiderivative of x squared. I'm going to integrate from 0 to 1. It's going to give me pi over 6, or approximately 0.524. For our next example, let's compute the volume of the region between the curves y and y squared minus 1 over the interval y between 0 and 1. And as always, if you don't necessarily know how to plot that, the curve y, or alternatively x equals y, is the same as y equals x. So that's this curve. And then y squared equals 1, if that were equal to x, I could solve for y, and that would say, well, y squared is equal to x plus 1, or in other words, y equals the square root of x plus 1. Square root of x plus 1 looks something like this. And so if I'm going to plot the region that's between those two curves as over the interval 0 to 1, we're looking at exactly this region, and we're going to rotate that region around the x-axis. So we're looking at something like this. And we're going to compute the area of that region. Now let's keep in mind that the volume here is going to work off of cylindrical shells, so we're going to have 2 pi RH. R in this case happens to be the height, which is exactly the value y, so we've got 2 pi y, and then h, the height of each cylinder, is going to be one curve minus the other curve, the upper curve in this case being the curve y, and the lower curve being the curve y squared minus 1 dy, and we're going to integrate over the range 0 to 1. If we simplify that out, we're going to end up with y minus y squared minus 1, or in other words, negative y squared plus y plus 1, distribute my y out front, I have negative y cubed plus y squared plus y, take an antiderivative, I'll have negative y to the fourth over 4 plus y cubed over 3 plus y squared over 2. On my bound 0 and 1, we end up with 7 pi over 6, or approximately 3.665. The last two examples here are going to be just like the first two, except I'm swapping x's for y's. So I have pretty good faith that everybody would be able to get those done if they had to. I'll move slowly enough through them to make sure that you can see them. But I did want to comment that we do have specific names for these methods, because in the first case, if we're slicing up our region with objects that look approximately like hardware washers, we call this the washer method. And this can be found whenever you have pi r squared dx or dy, because you're calculating areas of circles, right? The washer is approximately a circle that's filled in, so it's areas of circles, as opposed to the shell method. The shell method, because we're working with cylindrical shells, in this case we have 2 pi RH, because we're talking about the surface area of a cylinder, which is comprised of a circumference of a circle, 2 pi r, as well as a height of a cylinder, h. And so those are going to be the two methods, washer method and cylindrical shell method. And then I'm going to go ahead and finish off the entire semester, the entire text, with a beautiful paradox here that synthesizes a few of our ideas. This is called Gabriel's horn most often. Sometimes it ends up being called Torricelli's horn. We're going to work with it as Gabriel's horn. So this example is pretty nice. We're going to consider the curve defined by x comma 1 over x, or equivalently, the function f of x, which is 1 over x. Okay, so this function, everybody knows how to graph it. It's got these lovely vertical and horizontal asymptotes, and we're going to consider it over the interval 1 to infinity, so there's my 1, and then we're going to go out here to infinity. We're going to rotate it around the x-axis, and so we've got this sort of a shape. Kind of looks like a black hole singularity or something on its side. We're going to ask questions about the surface area and the volume of this shape. So if we construct the surface area formula, let's recall what that looked like. SA would be 2 pi integral r times the arc length, so root 1 plus f prime squared dx. Well, in this case, r is the function 1 over x, and then f prime would be its derivative, so 1 plus negative 1 over x squared dx. We'll integrate from 1 to infinity here, from 1 to infinity here. So there's my surface area. And if I simplify a little bit, I can pull my 1 over x to the inside at the price of a square on it. So you'll end up with 1 over x squared plus 1 over x to the fourth on the inside of a square root. It's not really something that you'll know how to compute right away, and we'll discuss what we might want to do with this. Meanwhile, if we want to construct the volume of this horn, the volume, at least using the washer method or the disk method, volume is going to be pi r squared dx, or in this case pi 1 over x squared dx from 1 to infinity, 1 to infinity. So volume is pi 1 over x squared dx, and we're just going to go ahead and try to compute and compare the surface area to the volume. Try to compute each of these and compare the surface area to the volume. Now in the surface area case, I did mention you're probably worried about how to compute that. But let's recall, this is an improper integral, so let's simply ask the question, does it converge? Should we use a convergence test to see? And I'm going to say, yeah, we should, because what am I thinking to myself? This is a square root of 1 over x squared. 1 over x squared is going to be a lot larger than 1 over x to the fourth, at least out near infinity, right? When infinity is a large number, 1 over 10 million to the fourth power is enormous compared to 10 million squared, but it's in the denominator, so this kind of falls out near infinity. It doesn't play much of a role. So if I look at the square root of 1 over x squared, that's approximately 1 over x. You can verify using the limit comparison test. So we use the limit comparison test of our integrand 1 over x squared plus 1 over x to the fourth with 1 over x. We can compute some limits on this. We end up with 1, which by the way is a positive finite constant. That says the limit comparison test is indeed valid. And we're going to be able to say that the convergence or divergence of the integral of 1 over x over this interval implies the convergence or divergence of actually the integral we're looking at for the surface area. But of course the integral of 1 over x is just log, and then if we plug in 1 at infinity, log at infinity is infinity. And so we have divergence of this integral, but the limit comparison test says we have divergence of this integral, and so our surface area has to be infinite. That's all fine, but then when we turn around and compute the volume, we can actually really quickly compute the volume of this object as the antiderivative of 1 over x squared, which is negative 1 over x, plug in our bounds of 1 and infinity. Well, we get negative 1 over infinity, that's just going to be 0. We're going to subtract pi times negative 1 over 1, we're just going to get pi as a volume. So we have a volume which is equal to pi, but a surface area which is equal to infinity for this particular mathematical object. In other words, we can fill Gabriel's horn by pouring paint into it, but we will run out of this paint if we try to paint its surface. Doesn't make much sense, right? If I poured paint into something, the paint is coating the surface, and I used a finite amount of paint. Well, what a way to end the semester to say, once again, mathematics is a game you win by making the craziest statement possible. There's only one rule. You cannot lie. See you somewhere, sometime, somehow. Bye.